Evening, everybody. We have a GCD problem. It stands for greatest common divisor. I've heard it called highest common factor also. GCD, greatest common divisor. Often this is left out and you just put the two values inside, make an ordered pair. But let's do like, I don't know, 21 and 14. The highest common factor or the greatest common divisor, synonymous phrases, for this particular problem would be 7. 7 is the largest divisor of 14 and 21 combined. Nothing bigger than that divides both of these except 1. Now we're supposed to prove, this comes from Sierpinski's 250 problems. I think it's 51A. I'll put it in the description if I can remember. We're supposed to show there are an infinite number of positive integers, positive integers, I didn't write that down, such that the greatest common divisor of n and 2 to the minus 1 is greater than 1. Now, another way of saying this is not coprime, or not relatively prime. I think coprime is supplanted relatively prime these days, but this means the same thing as not coprime. And of course, the two arguments don't have to be prime. It's just a manner of speaking. Okay. Now, so it's real easy to check these first 5 cases, and that's why this problem, I guess, is quote interesting. They're relatively prime for n equals 1. Like if n is 1, you get 2 minus 1 is 1. GCD of 1 and 1 is 1, of course. If you put 5 here, you get 2 to the third, 32 minus 1. 31 is prime, and then 5 is prime, and they're relatively prime. And you can check for the others, all right? Now, when you get to 6, though, you actually get a greatest common divisor of 3, which is greater than the 1. So 6, the integer 6 is of interest here. Again, this is easy to verify right here. It's equal to 3, which is greater than 1. So what we can do is work with this number here as a candidate. Rather than just 2 to the 6, we make this 2 to the 6k, where k is any positive integer, an infinite number note. Okay. Now, just, a little bit of algebra, you know that you can rewrite this as 2 to the 6th raised to the k power. It's k copies of 6 copies. Like that, all right? Now, this next result, it may not look particularly familiar, but it's just the result a to the n. Let's do, I guess we can do a to the n minus b to the n if you want. It's in the form a to the n minus b to the n, where a is equal to 2 to the 6th and b is equal to 1. All right, and of course this form is like this, and this is also related to geometric series, finite geometric series. You have a minus b as your first factor, and you get kind of a telescoping sort of behavior. Okay, so the next one would be what, a to the n, I guess. A to the n minus 1. The very first term would have to be a to the n minus 1. The next one, let me write down beneath here, a to the n minus 2, a to the n minus 2b. And again, b is 1 for our problem, which simplifies matters immensely. Sorry, this is, as usual, out of space here. Plus ... plus b right here at the very end. So what I've written down here below is really just a special case of this where b is equal to 1. Again, a equal to 2 to the 6th and b equals to 1, and this is what you would get. Now notice this is really nice here because we have something we know. We know that 3 divides s for all k, divides s since 3 divides the quantity 2 to the 6th minus 1. And again, that's 2 to the 6th, as I never did, is 64 minus 1 is 63. And we did this at the very beginning, okay? So you see what this proves for us 3 divides this for free. We don't even know anything about what's going on over here, but it's okay. We have a 3 right here dividing this factor of s, okay? And so what we have shown is that the GCD, let me write it right here. The GCD of S okay, and then what do we need? Well, I wrote it backwards, but the GCD of S and N, I'm going to say greater than or equal to 3 because it may be bigger for some of them. I don't know, but we didn't. It's not important. It's not going to be coprime. Okay, for k equals 1, like you've seen, k equals 1, 2, 3, countably infinite, right? Remember, the S depended on k right here, all right? And so that proves it, QED. Now, again, folks, it's easy to lose track because I don't keep everything on the same screen. But we wanted to show there's an infinite number of n such that this is true. So we just did that by considering this object right here, okay? It worked out very nicely just by considering this for our S, okay? So that takes care of business, folks. Let me know what you thought.